Alright, in this video we'll be looking at hydrocarbons, specifically alkanes, and how to name them. So again, we have hydrocarbons. Hydrocarbons are molecules that are made up entirely of hydrogen and carbon. So there'll be no other elements in the hydrocarbon. Hydrocarbons are classified into 4 different categories depending on their molecular structure. We can have alkanes, alkenes, alkynes, and aromatics. Alkanes contain only single bonds. Whereas alkenes contain at least one double bond. And alkynes will contain at least one triple bond. And aromatics will have a special type of ring, usually a benzene ring. Although other types of ring can be aromatic. So in this video, we'll focus on the alkanes with the single bonded hydrocarbons. So again, alkanes contain only single bonds. And another way to describe them is saying that they are saturated. That means they are saturated with hydrogen atoms. That they cannot hold any more hydrogens. That if we were to describe their molecular formula, it would be CnH2n plus 2. That if we have, like, say, 3 carbons, then it would be C3, N would be equal to 3, so C3H2n 6 plus 2, 8, C3H8. And I'll write that as an example. Now, because all of the bonds in an alkane are non-polar covalent bonds, alkanes are non-polar molecules. And that means that they are held together only by London forces rather than by hydrogen bonds or dipole interactions. And so small alkanes like methane, ethane, they don't have a lot of surface area because they're small molecules, and so the London forces that hold those molecules together are very weak, and so they have very low boiling points, and so they become gases at room temperature. In fact, the first four of the normal alkanes are gases at room temperature. So that would be methane with one carbon, ethane with two carbons, propane with three carbons, butane with four carbons. Once we get to pentane, the fifth alkane, um, then pentane through heptadecane, which is the 17th alkane. So 5 carbons with pentane, 17 carbons with heptadecane. These would be liquids. And if it's 18 or above, then they'll be solids at room temperature. And so as the alkanes become larger, we have stronger London forces holding those molecules together. And so their boiling points and their melting points go up. So that by the time we get to 5 carbons, it's a liquid at room temperature. So the boiling point is lifted above room temperature. And by the time we get to 18 carbons, the melting point is above room temperature as well. And so they're solid. I should also point out that all alkanes will have a tetrahedral configuration at every carbon atom. So if this is a methane, we can see the tetrahedral shape of that molecule. That we've done labs where you've looked at different molecular models and determined the shape of based on the Lewis structure. And so you should know what a tetrahedral molecule looks like. And when we have even larger alkanes, such as this hexane here, 1, 2, 3, 4, 5, 6 carbon atoms, that makes this hexane. That around each carbon is a tetrahedral orientation. And so it's just, even though there's more than one carbon here, it's all has the same tetrahedral structure around each individual carbon. And so where do we get alkanes? What is the source of for alkanes as chemicals? Well, the source of an alkane is usually petroleum, crude oil. So petroleum is a mixture of many different organic molecules, mostly alkanes. And we generally separate these alkanes according to their boiling point using distillation, or fractional distillation to be more specific. And so that we'll have these large towers, and there'll be several plates within each tower. And petroleum will be fed into the bottom of these towers, and it'll be heated up very hot. And the stuff with the molecules with the highest boiling points will sort of be collected out of the bottom, and that includes your things like asphalt and tar. These very high melting point petroleum products, and so these make good things for like roofing material or road construction material, but they don't make good fuel or anything. And then we'll see that at a higher boiling point, we can collect not at a higher boiling point, a lower boiling point, but at a higher position in the tower. As we go up in the tower, the temperatures become cooler, and so we'll get like fuel oil, which is liquid enough that you can burn it for fuel. It's not a very high grade fuel, but it is usable. Then we'll see diesel. I'm not sure I'm spelling that right. Anyway, after diesel, we'll get kerosene, gasoline, and then the coolest temperature we'll get like propane, butane. And so these molecules generally become smaller as their boiling point gets cooler. And so we have very large organic molecules down here in the asphalt and tar region. And then as we go up to fuel oil, to diesel, to kerosene, to gasoline, to propane and butane, the alkanes become smaller and smaller. So that because there's less London forces holding them together, they have lower boiling points. And so they will remain a gas in these cooler temperatures as they move up the tower and cool down. So that's how we get our alkanes and other hydrocarbons from petroleum. And so if we ever run out of cheap petroleum, which is likely at some point in the future, we don't just have a problem, how do we fuel our vehicles, but where do we get many of the chemicals that are used in for making plastics and pharmaceuticals. And so petroleum is important for more than just fuel. I should also point out that it is possible to convert heavier fuel mixtures, heavier mixtures of alkanes, to lighter mixtures of alkanes using catalytic cracking. And so cracking is the process by which we can take a large organic molecule, like let's say fuel oil, and we just heat it up in the presence of a catalyst to convert the fuel oil molecules, these large alkanes. We break them up into smaller alkanes, and so we can convert this fuel oil mixture into a gasoline-like mixture. And this is important because petroleum doesn't contain enough gasoline to meet all of our demand for gasoline. And so we can convert some of this heavy fuel oil into lighter weight gasoline through the process of catalytic cracking. And that will provide enough gasoline to meet the demand. Anyway, now that we've gone over some properties of alkanes and where alkanes come from, we should discuss how alkanes are named. And when it comes to naming straight chain or what we call normal alkanes, it's fairly easy. The normal alkanes, because they have no branches, they're named entirely based on the number of carbon atoms in the alkane. And so if we look at the number of carbons, 1, 2, 3, 4, 5, 6, 7, then it will start methane. With 2 carbons, we'll have ethane. With 3 carbons, it'll be propane. With 4 carbons, it would be butane. 5 carbons, pentane. 6 carbons, hexane. 7 carbons, heptane. If we continue the table over here with 8, 9, 10, then we would have octane, nonane, and decane. And so these first 4 have a little bit unusual names, that it's methane, ethane, propane, butane. After we get through these first 4, the names are all based on the numbers. For pentane, 5, hexane, 6, heptane, 7. And so if you think of a pentagon, a hexagon, a heptagon, an octagon, then those numbers correspond to the number of carbons in the molecule. And so with normal alkanes or straight chain alkanes, the names are all fairly simple. We take this prefix that corresponds to the number, and we add A-N-E, ane, to the end because it's an alkane. And so this tells us, for example, if we were given the name nonane, we would know that it's an alkane based on the ane ending, and it has 9 carbons because of the known, the non prefix. And so we can determine its molecular formula from the name, because we know that alkanes have the formula CnH2n plus 2. So if we're giving nonane, it's C9H20, because that's 2 times 9, 18 plus 2. But of course, not all alkanes will be normal alkanes. There will be many times when we're given a branched alkane, and when we have branches, the rules for naming those molecules become a little more complex. So naming branched alkanes. The first step will be to identify and name the parent chain. And so this parent chain is the longest continuous chain of carbons. And so you'll have to look at the molecule and look at all the different chains of carbons and figure out which one's the longest, and that will be the parent chain. If the parent chain contains 6 carbons, then the parent name of the molecule will be hexane. If it were 5 carbons, it would be pentane. If it were 4 carbons, it would be butane, so on and so forth. Then we have to name the alkyl groups attached to the parent chain. And so we have to look at all the branches that come off of this parent chain. We have to give each branch its own name so that we know we can identify the different structures that come off of that parent chain. And then we have to determine the position of those groups on the parent chain and assign each position a number. And then once we have the numbers, we have to also look at if we have more than one identical group, so when more than one identical group is present, we have to use di, tri, tetra, penta, etc. To specify how many of that group we have. And so the overall name of the molecule will have this all of this information: the name of the parent chain, the names of the alkyl groups, the numbers where those alkyl groups can be found on the parent chain, and prefixes to tell us how many of each group exist attached to that parent chain. And we'll work through several examples in order to help understand how to use these rules. So our first example and I'll color code this the molecules to make identifying what part of the molecule fits what part of the name a little more easy. And so with this molecule, we have one branch, and this black part is the main chain. It contains 1, 2, 3, 4, 5, 6 carbons. And so we know that it will be a hexane. That is the name of the parent chain, hexane. So now we need to identify the branch. It is a single carbon, And so that one carbon is a methyl group because of the meth prefix. And so we know that it's a methyl hexane. So methyl hexane. Now we need to identify the number, the position on the parent chain. And so we always start numbering at the end of the chain that gives the smallest numbers. And so we'll start here on the left. 1, 2, 3, 4, 5, 6. So this methyl group is on carbon 3, and so it becomes 3-methylhexane. That's the name of this molecule. If we started numbering on the other side, 1, 2, 3, 4, 5, 6, then it would be 4-methylhexane, and that name wouldn't work because we wouldn't have the lowest possible number. We want that lowest possible number for our groups, and so we choose to number here from the left so that we get 3-methylhexane instead of 4-methylhexane. So the next example, okay. On the next example, we have 2 branches. And so again, we identify that main chain, and that's this black region, this black part of the molecule, 1, 2, 3, 4, 5, 6, 7. And so with 7 carbons, our main chain will be a heptane. Okay. And so now we look at our 2 branches, this blue branch and this red branch. This blue branch contains 1, 2 carbons. Well, with 2 carbons, that's an ethyl group. And so just to specify, I will write that down. Ethyl. And again, we have a single carbon in this red branch. And so that's methyl. So now, how do we number these molecules? Again, we start at the end that gives us the smaller number. And so if we start here on the left again, we have 1, 2, 3, 4, 5, 6, 7. And so with these 7 carbons, we would have a 2-methyl, 3-ethyl. If we started at the other end, it'd be 1, 2, 3, 4, 5, 6. And 5 and 6 are higher than 2 and 3, so we choose to use the end that gives us the 2 and the 3, the smaller numbers. But what order do we place the ethyl group and the methyl group in the name? And we go not by the position in the molecule, but by alphabetical order. And so because ethyl starts with E and methyl starts with M, we choose to put the ethyl first. So it becomes 3-ethyl, 4-methylheptane. And so you may have noticed I'm using hyphens to separate the numbers from the different parts of the name. So 3-ethyl, -4-methyl, that we use those hyphens to separate the numbers from the words. We don't use a hyphen to separate the prefix. And so it just goes methylhexane, methylheptane, no hyphens in between the methyl and the hexane or the heptane. The next one will get a little more complex. One, two, three, four, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 1, 2, 3, 4. Now we have 3 branches. And one of those branches has branches of its own. And so we'll go ahead and identify the parent name of this molecule. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbon atoms. And so that makes it a decane. And we'll need plenty of room for the rest of this name, so I'm going to put it over here. So this is a decane because our parent chain has 10 carbon atoms. We know that this group here with 1, 2 carbon atoms is an ethyl. This blue branch with a single carbon atom is a methyl. But what about this orange branch? It contains 1, 2, 3, 4 carbon atoms that are branched. So it's a branch with branches. And it contains 4 carbons. And so it's a butyl. But it's a specific kind of butyl group. It's what we call T-butyl or tert-butyl. It's short for tertiary butyl group. And that's because this carbon here has this 1, 2, 3 other carbons branching from it. And so it's I guess technically it's a quaternary carbon because it has a total of 4 carbons attached when we look at our decane. But if we just look at these branches in this orange group, then it's only got these 3 branches, so it's tertiary butyl or tert-butyl group. And now here's another funny thing about naming is when we have groups that are specified as tert-butyl with this T hyphen, we ignore that T when it comes to alphabetical order. And so tert-butyl begins with a B. And so, again, we'll name these groups in the overall name in alphabetical order. And so it becomes tert-butyl, ethyl, methyl, decane. And now let's identify the numbers so we know where each of these branches are in the molecule. So if we start from the right this time, should just buy some better markers. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have a 4 ethyl group and a 6 methyl group and a 6 tert-butyl group. Because both of these branches are attached to that same carbon, we use the number 6 twice. So that would be 6 T-butyl four ethyl 6 methyl decane. And I didn't get the names to line up properly, but it should be readable. 6-tert-butyl, 4-ethyl, 6-methyl-decane. And so as the molecules become more complex, these official chemical names become much more complex with it. And so we've got a few more examples that we should work through just to get the hang of this, because naming molecules is an important skill in organic chemistry, and it's one that requires quite a bit of practice. Two, three, four, five, six, seven. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. So in this example, our parent chain contains 1, 2, 3, 4, 5, 6, 7, and so it's a heptane. And we have 2 methyl groups now. So we have 2 identical branches located at positions 1, 2, 3, 4, 5, 6, 7, located at positions 3 and 4. And so when we write this name to specify these positions, we will use 3, 4 hyphen and then dimethyl heptane. And there shouldn't be a space here. I just didn't get the words aligned properly, but it should all be one word, dimethyl heptane. And we use this di group, this di prefix, to specify that there are 2 methyl groups. All right, so in this example, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. And so it's an octane. And we'll number it. Let's start from the left this time. 1, 2, 3, 4, 5, 6, 7, 8. Then we have 2 methyl groups again. And an ethyl group. And so you might think, because this is dimethyl, it starts with a D, but no. Again, we ignore this first letter for alphabetical ordering purposes, and we go with the M. And so dimethyl starts with an M. And so again, the ethyl comes first. It's at position 5, 5, ethyl. Then our methyl groups, they're both on carbon 3, so we use the number 3 twice. 3, 3, dimethyl octane. And I really gotta work on lining these words up better. But anyway, this molecule becomes 5-ethyl 3,3-dimethyl octane because of these 2 methyl groups at position 3 and this 1 ethyl group at position 5, and that the overall structure, the parent chain, is an octane. Uh, so in this example, the branches aren't really drawn to scale because I've run out of room. But we have 1, 2, 3, 4, 5, 6, 7, 8. And so this will be another octane. And we'll go ahead and number it. 1, 2, 3, 4, 5, 6, 7, 8. And this time we have another methyl. Because we have this single carbon here, so it's a methyl group. Well, what about this? We have, it's another branch with a branch of its own. It has 1, 2, 3 carbons, and so it's a propyl group. But because we're attached to this middle carbon, we specifically call that an isopropyl group. And to further confuse things, if you remember how the T in tert-butyl was not included in the name when it came to alphabetical ordering purposes, and so tert-butyl starts with a B, isopropyl starts with an I. That this prefix is included for alphabetical ordering purposes. And you'll notice that in tert-butyl, if you go back and take a look at that, I wrote that T-butyl, that there's no hyphen in isopropyl. It's all one word. And so we use that I as our letter for alphabetical ordering. Whereas with tert-butyl, because it's hyphenated, the T is ignored for alphabetical ordering. And if you don't like it, you can bring it up with the International Union of Pure and Applied Chemistry because they're the people who come up with these rules. But anyway, when we go to name this molecule, this I comes before M. So the isopropyl group will come first in the name. So 5-isopropyl 3-methyl octane is the name of this molecule. Let's go with the simpler one, I think. If I can draw it. Two, three, 4, 5, 6, 7. Okay. So now we have 2 methyl groups again on a 1, 2, 3, 4, 5, 6, 7. So this is a heptane. That will be our parent chain. And we'll number it 1, 2, 3, 4, 5, 6, 7. And so we have these 2 carbon atoms, these 2 methyl groups, on carbons 2 and 4 of the heptane chain. And so this becomes 2,4 dimethyl heptane. So that was a couple more examples. We've still got a few examples to go. So now we have two methyl groups and an ethyl group on a 1, 2, 3, 4, 5, 6, 7, another heptane chain. And again, the ethyl comes first alphabetically. Oh, wait, let's number this 1, 2, 3, 4, 5, 6, 7. So the ethane at position 5 comes first. 5, ethyl. Then our two methyl groups at positions 2 and 3. So 2, 3, dimethyl heptane is the name of this molecule. So actually the last example I've got on my notes. I highly recommend that you go through the problems in the book at the end of the chapter so that you get more practice with how to name these molecules, because it does take quite a bit of practice in order to identify the different groups and get the hang of the numbering and how to write the all of the different parts. One thing I should do before I end the video, though, is to go over different structural groups so that you can identify them more easily. That I'll just use a squiggly line to represent the large part of the molecule. And so then I'll just show the branches as they come off. And this information can be found in table 8.3 in the book. Okay, so again, we have a single carbon as our branch, and so that's a methyl group. Now we have two carbons as our group, and so that's an ethyl group. And there are no other ways to arrange a methyl group or an ethyl group because we only have one carbon, so there's really only one combination of one carbon. The ethyl, again, we only have two carbons. There's only one way to arrange these two carbons. But once we get to 3 carbons, then there are 2 ways of arranging those 3 carbons. We can have all 3 carbons in a straight line, 1, 2, 3, and that becomes a propyl group. Or we can have a branch. And so now we have 3 carbons again, 1, 2, 3, but we connect to that middle carbon. And so that is the isopropyl group. If we come over here, we have 1, 2, 3, 4 carbons in a straight chain. That is a butyl group. If we connect to the second carbon in that chain instead of the first. So here in butyl, we're attached to carbon 1, then 2, 3, 4. In this group, we are attached to carbon 2 rather than carbon 1. This becomes sec-butyl or S-butyl. And you'll notice we have a hyphen here, and so separating the sec from the butyl, and that means that for alphabetical ordering purposes, it starts with a B. Whereas with isopropyl, it starts with an I. And I don't know why they decided to do that. It's just the way that the system is. And then finally, if we have, again, this is a butyl group. We have 1, 2, 3, 4 carbons here. And so, but this specific type of butyl group is a tert butyl or T-butyl, and because of this hyphen, it starts, for alphabetical ordering purposes, it starts with a B. And so this is just a small selection of the different alkyl groups that we'll see on organic molecules, but these are the ones that come up most often. And so these are good to know: methyl, ethyl, propyl, isopropyl, butyl, sec-butyl, and tert-butyl. So knowing these different groups and their names will help when it comes to naming organic molecules. And so with that, I'll go ahead and end this video.